Okay, well, again, thank you for Guy for inviting us along today. We've sort of split the presentation into two, so we're a bit limited in time, so if I talk fast, you'll have to bear with me. So Jason and I are both technical support engineers. In fact, we're the only technical support engineers in South West Water, so everything could be going pear-shaped back down in Devon. Mobile phone switched off. So. One of the responsibilities of my team is to deliver an enhanced pressure management programme for South West Water over K5 and K6. The reason we need to do this, South West Water has one of the highest average zone night pressures in the UK water industry at around about 59.5 metres or just under 6 bar. So great potential for overstressing our pipelines. Despite that, we are recognised as industry leaders in leakage control and management. But our success in this area is built largely around detection and repair techniques. It's an expensive way to manage leakage, and we recognise that in order to reduce the cost of this, we've actually got to intervene at an earlier stage and actually start taking pressure out of our system to reduce the stress on our networks. The way we propose to do this through our pressure management programme is we've got a target to reduce our AZMP by 10 metres or 1 bar across this and the next AMP period, which is a fairly ambitious target. But we believe that by achieving that, we should reduce our burst numbers and our leakage levels by about 14%. And based on last year's June return data, that would equate to somewhere around a reduction of 400 repairs on our network. And as Jason and others have alluded to, there would obviously be a significant SIM impact if we were able to achieve that. So we're going to look at just 3 technologies that we are using to help us to achieve our pressure management objectives. So we're going to look at advanced pressure control, the I2O system, which has been referenced various times today. We're also going to look at some almost brand new smart metering technology developed by Clayval Europe, and also, which again I think is relevant to some of the discussions here today, green energy capability from pressure control. So, as Jason showed on one of his earlier slides, we have around 2,000 pressure-reducing valves already in the ground at South West Water. So, pressure management isn't new to us, but our pressure-managed areas are far from optimised, and the majority of those we've used fixed outlet settings on our PRVs to basically to make a step change in pressure in our networks, but it's far from fully optimising the network. So what does that look like? Well, in this example here, P2 would be the fixed outlet setting on our pressure reducing valve, in this example around about 45 metres, and we've determined that we need that much pressure in our system in order to make sure at peak demand period that we achieve our target pressure at our critical points, which are usually the highest points towards the extremes of our network. So you can see that that setting is relevant for that point in time, which is a very brief period, a peak demand period, usually around breakfast time. But across all other points of the day, when our system demand reduces and our system head losses are reduced, we're exposing our network to much higher pressure than we really need to. So what do we do about this? Well, we've implemented our first system using the I2O process, which works by actually sending pressure data collected from our critical points from inlet and outlet of our pressure reducing valves, and also flow data referencing the amount of water that's passing into each of our PMAs to a hosted data centre which I2O manage on our behalf, and they look at the relationship between those various bits of data to actually determine what the optimal setting for our PRV should be. That information is then transferred back to a controller that's installed in the PRV chamber, and that using sort of daily algorithms computed from that information, it instructs the advanced pilot valve that sits on top of the PRV to determine what the PRV profile, outlet set point profile, should be across the course of a day. So by doing that, what we achieve is that we've now got a much tighter critical point pressure, and we achieve that by varying the downstream pressure on the pressure reducing valve. And our excess pressure zone then becomes almost negligible. So we're optimising the network through all points of the day. And this is, again, data provided, sample data provided by I2O, but it just shows an implementation phase of one of these systems. So we see over here on the left-hand side that we've got just a step down in the fixed point pressure with reference to the critical point. And in the middle zone here, when we start to introduce flow into that scenario, we can see that we're beginning to get much tighter control over our critical point pressure, and through continuous optimization we've almost got stable critical point, and we then see the slight variability on the outlet of the PRV, but nevertheless significantly lower than the pressure that we started with. So one of the issues for South West Water is of those 2,500 existing PRVs that we have in the ground, very few of those were installed with meters. So we're missing that key component, which is the flow data into the network. So in discussion with one of our companies that we use in our supply chain, Clayval, they've developed a clever solution to this, which is their e-flow meter. And as you can see in the picture there, the e-flow meter actually bolts straight into the side of the PRV in a spare pressure port. And this avoids perhaps expensive excavations and chamber builds in order to supply a meter to support that network under traditional means. And certainly in some of the urban networks, we've got very congested highways, so perhaps there isn't even space to provide that traditional new chamber and meter. So the way this system works, and say I think this is brand new technology. I don't know whether any of you have seen it before. It's I think patent pending still for Clayval, but the actual system works by within the head of the meter. This part here, there is a bluff plate which actually sheds downstream vortices, and those downstream vortices are measured as left and right hits on a piezoelectric disc, which is also installed within the branch here of the meter, and the rate of hit is directly proportional to the velocity flowing through that meter. So this is kind of what it looks like. You see a left and right hit here, which is equivalent to one period, and 200 left-right hits are equivalent to a frequency of about 100 Hertz, which is equivalent to a velocity of 1 metre per second of flow. Clayval have tested this meter in their own test facility at Lausanne, and this graph just shows, I'm sorry, the resolution's not very good on that, but it shows the comparison between the e-flow meter and a typical ultrasonic meter, and you can see we've got a very, very close match. And Clayval claim an accuracy full scale for the e-flow meter of better than plus or minus 2%, and these results have been independently verified by Imperial College London and Utah State University, so we believe it's a very accurate piece of kit which will serve us well in terms of providing that missing flow data provision into our pressure managed zones. So, having now found all this nice equipment that we can use to support us in our pressure management objective, we have to power these sites, power the data recovery from these sites, and traditionally the way we would do that would be either to supply electricity supply to the site. Electricity tariffs are rising. The cost of electricity connections, particularly on rural networks, is prohibitive. The alternative perhaps is batteries, and we've already said various times today that battery life is poor, and I think if you want quick data, high resolution data, then batteries on their own are not the answer. So Clayville have come up with a possible solution to this using the power of water that we break across the PRV to provide a solution. So they've come up with 3 e-power units. The lower power unit here will produce something in the order of 750 milliwatts of power. It needs a pressure differential of around about 6 metres in order to create that, and at a flow of around 6 litres per minute. This unit would, for example, power a data logger producing data at 10-second resolution and data transmission every 15 minutes. So you could certainly, it's almost capable of real-time data provision. On the other end of the scale, we've actually installed one of these at one of our sites at Helston Bench on Dartmoor, and if you know Dartmoor, it is in the middle of nowhere. It's probably 2 to 3 miles from the nearest community, so there was no question ever of providing electricity supply to that site. But the high power unit will produce up to 240 watts of power. It requires a pressure differential of between 20 and 40 metres and a flow of 75 litres per minute to produce something in the order of 12 to 24 volts DC. This particular unit we're using to operate a power drive controller on top of one of our PRVs here. It also powers my master meter and the data that we recover from that. And it also heats the chamber for us, so it stops it from freezing up during the winter months. So those 3 technologies together, we believe, will enable us to deliver our pressure management objectives through this and the next AMP period. And that concludes my presentation. Thank you for listening. I'll take any questions.
Thank you very much, Myles. Are there any questions on what Myles or indeed what Jason has been presenting to us over the last half hour? Yes.
How many of those 42 deployments are you intending to install?
We haven't because it's brand new, hot off the press. I mean, our programme was built principally around new installations, so we were looking at installing another 500 installations where actually at the time when we put the cost benefit together we weren't even aware of this technology, so we were actually looking at opportunities for installing large chambers with meters and PRVs in them, but we now recognise the ability to retrofit these to existing chambers to actually enable us to optimise a lot of our existing systems as well as installation on new. So we haven't determined the number yet, but my guess would be that we would certainly be looking to install them on our 500 new installs at least.
Roughly what do you think the cost again on those end
I can't give you a figure for it. I mean, I think in terms of the actual cost of the meter install, the meter is at a similar price to an ultrasonic meter, but of course you're saving on the cost of the excavation and the chamber build. I can't put a price at this stage to the data recovery from that.
Before coming across this new technology, were you planning on deploying flow pressure meters onto the inlets in your network?
Certainly on the new installations, we recognise that there was a need to do that, yes.
And on the old existing ones? On all DMAs? Or
no, we haven't. We haven't seen the... again, I2O is fairly new technology for this. Again, when we built our business case for pressure management, we were looking at new installations rather than optimising old. And we now see that for the financial provision we've got for this, we can do an awful lot of additional work through these new technologies in terms of improving what we've already got.
Yes.
How are you receiving the data?
from remote sites?
At the moment, certainly for the I2O system, the data is actually hosted by I2O, so the data transmission is to I2O over GPRS networks, and then that information is returned to the controller in the same fashion.
Any further questions? Good. Well, thank you very much indeed, Myles.